Bon, donc on a le plaisir d'accueillir aujourd'hui Giulio Biroli. Donc, je vais faire le séminaire va être en anglais, je pense. Je vais faire une brève présentation de Giulio, que beaucoup d'entre vous connaissent. Donc, Giulio a fait ses études de master à l'école polytechnique. Et puis ensuite, une thèse en France et un postdoc. Une thèse en France dans le domaine de la physique statistique du système désordonné. Ensuite, un postdoc à l'université de Rutgers. Il est ensuite revenu en France sur un poste du CEA à Saclay. Et depuis quelques années, il est professeur à l'école normale supérieure. Giulio est très connu pour toute une série de travaux, en particulier dans le domaine de la physique statistique des systèmes désordonnés, des contributions remarquables sur la dynamique des systèmes vitreux, entre autres. Mais aussi des travaux sur les systèmes quantiques. Et depuis quelques années, il s'intéresse de très près à toutes ces méthodes d'apprentissage et de réseaux de neurones. Je crois même que vous avez créé à l'école normale un centre, c'est quoi, le Center for Data Science, c'est ça, avec Stéphane Mallat et autres. Il a mis à profit toutes ces approches de physique statistique pour comprendre mieux comment fonctionnaient ces méthodes d'apprentissage. Et donc c'est un peu le sens de ce séminaire, qui est de prendre un peu une récréation par rapport à l'optimisation des fonctions d'onde quantiques et d'avoir un peu une fenêtre sur la manière dont ces réseaux de neurones fonctionnent pour mieux comprendre ces machines qu'on ne comprend pas très bien. J'ai déjà recommandé aussi dans mon premier cours un très autre bel article de Giulio, dont il ne va pas parler aujourd'hui, je pense, mais qui était cette transition de jamming entre le régime de sous-paramétrisation et de surparamétrisation et le lien avec les systèmes vitreux. Voilà, donc Giulio, je te laisse la parole et tu vas nous parler de groupes d'Renormalization et de machine learning.
Merci beaucoup. Thank you very much. So it's really a pleasure to be here. So indeed, today I want to discuss, to address some questions which are really related to why this method works. So you can see, it's as Antoine explained in his lectures. So this method are a way to parameterize a function of many variables, or if you want, a many-body wave function, or a many-body probability distribution. In computer science, it's more a probability distribution that they call in high dimension, because you have many variables. And the question is, why can you do that? Why these representations are good? Why they work? And so what I'm going to do today, I'm trying to answer this question for problems in physics. There will be no quantum mechanics, but hopefully, maybe there will be some ideas that can come up, trying to generalize what I explained today. So yes, so these are my collaborators. So Stéphane Mallat, who is at the computer science department at the École Normale, and Professor at Collège de France, who gave lectures indeed on machine learning and statistical physics this year, and on machine learning before. And then very two bright, they were postdocs, but now Misaki Ozawa is a CNRS researcher, and Tanguy Marchand is in a private company. All right, so Antoine already explained a lot about machine learning, so let me recall something about, let's say, revolution. There are many revolutions in machine learning, but one, for example, one case in which you see the power of this machine are generative models. So there have been many that have been introduced. The latest one are diffusion models. So generative models, what they do is they can create data which has a which are meaningful. So in particular, for example, if you think to images, what is well known is that they can create, images that they look like standard images, but, they are completely invented by the machine. So for example, if you train a machine on cats, images of cats, they can transform, roughly speaking, white noise, in an image of a cat that does not exist. Same thing for the faces. Here, just for fun, I asked actually DAL-E to create a fake Giulio Biroli, and here is what you see. The result is debatable, but okay, this is what you can do. And so what they do is, again, as was discussed by Antoine, the kind of structure that they have are based on successive nonlinear transformation, in which, in general, you have some data then you apply some linear transformation with the matrix, then a nonlinear transformation, and then you go on. So they have a kind of hierarchical structure in which you have successive nonlinear transformation. So in principle, they can parameterize arbitrary complex function, but they do it in a specific way, which is this concatenation of different layers. Now, what I want to do is, I want to stress, and well, I think you are convinced now, is that they have a lot of interesting application in physics and potentially even more. So there are, I think, two kinds of application that one can discuss, that have been discussed. One is representing many-body function. So in the case of context system, quantum system, as Antoine discussed a lot, is you can represent many-body wave function, which are a function of many variables with neural networks. You can, if you are interested instead on classical physics, in statistical physics, you can, and you have, for example, an equilibrium system or an out-of-equilibrium system, you can represent the probability distribution of the system, which is a function of many variables. So this has been done, for example, for simple cases. This is a configuration of the Ising model. This is actually a configuration of the projected density of the universe. This is something on which Stéphane Malat with the group of DNS work a lot. So, I mean, this just to say, there is one direction which is this, of course, in physics, in many cases in which we cannot solve the problem, we want to have an approximation, a way to approximate this function of many variables. This function can be the wave function or the probability distribution. And this machine allow us actually to do this in a very meaningful way. There is another actually very interesting direction of research, which is new ways of sampling. So as you know, I mean, when you do physics, in general, you want to sample configuration. If you are in statistical physics, well, you use Monte Carlo Markov chains, for example, to sample new configuration of a problem. And also in quantum system, sampling it's a very important problem. And one very big difficulty with sampling is that sometimes it takes an extremely long time actually to sample uncorrelated configuration. And now this machine, I mean, the idea is that, well, exactly if you can transform white noise in a phase, and then you can get many different phases from many different white noise, and you can do it very fast. Maybe they can do the same thing in difficult problems, in which a standard Monte Carlo Markov chain would take a long time to equilibrate. Maybe they can just give different uncorrelated configuration is what is called one-shot. And this is just, well, this is a paper that tried to do this in the case of protein folding. I mean, all this, I would say, is not a solved problem, but there are indications that this machine can be useful to try to, maybe not to solve, but at least to make a substantial problem in the direction of sampling. So there are really potential groundbreaking applications in science, but at the same time, I think there are very important questions which are, I mean, why does it work? And to be more specific, let me list the questions that one can ask in science for the application in science, but more generally also for the application in computer science. So the first thing is, of course, while there are, I mean, this machine can represent function of many variables, but you can ask, okay, how faithful is the representation, for example, of a probability distribution if you are in a statistical physics problem? So yeah, you have many parameters, you have many parameters to fix, but then what you get, how faithful it is, and it's clear that there is a trade-off between expressibility, the number of sample, and the interpretability. So this is clearly a question that, yeah, you increase the number of parameters, you increase the number, I mean, the space of function that you can represent, but then, I mean, when you use this machine, what kind of actually system you're representing? There is a clear question about training efficiency and scalability in the sense that it seems that, and there is some magic in the sense that you have, I mean, it's not even billions, it's billions of parameters now in some machine, and you can train them without any problem. And how this is possible, actually, it's an open question, why the system does not remain stuck in bad solution. Then you can also ask, imagine that you want to solve a problem of statistical physics with, I don't know, 10,000 particles using this machine. Now, if you multiply by 10 the number of particles by 100, are these machines still going to work, or there is some problem in scaling up? And well, there's the question about sampling. Sampling, so exactly as I told you, you can generate new configuration. Now imagine that you have a problem with slow dynamics. Are there some inherent difficulty in sampling using this machine or not? Or maybe they can really sample very fast, as I mean, some work seems to indicate. And then the other question is really, why does it work? And I think, I mean, there are two. One has to think about that this machine, in principle, they can represent any function. This is what is called the universal approximation theorem. However, there is a big but on this. It's true, but in principle, the number of parameters that you should use if you want to represent any function should go like the exponential of the dimension of the input. And if you consider the normal input that, for example, for an image, I mean, even small images are something like 1,000 pixels, so exponential of 1,000 would be a very big number, and the number of parameters that are used are much less than this. So in principle, they should always work, but then if you wanted to make them work on realistic application, the number of parameters would be just impossible to treat, and so they still work. So why so? Why are they able actually to work? And it's clear, and this was actually someone asked this to, I think, Karaskila, if I remember correctly, is that it's clear that there is some inductive bias. There is something that is put in this machine that is related to the kind of data that this machine uses. So they are not black boxes that can work for any kind of data. So somehow, in the structure of the network, of the deep network that are used, there is something that is related to the data that this machine are using. And this is why, this is the big question and the things that one should understand why they work. Otherwise, I mean, again, there is no magic. I mean, it cannot be true for anything. Yes?
To me, this universal representation theorem is a little bit like the ergodic theorem in StatMech, right?
Yes.
It is something which is nice to have, but which is not the reason why StatMech works.
Yeah, yeah.
So isn't it a bit like this here as well? I mean, fundamentally, why this work is very vague, what I'm going to say, but some sort of central limit theorem that states that you don't need to explore this enormous number of configurations. I mean, we know we don't have to do that for StatMech to work, right?
Yeah.
So is there something similar?
I think it's yes, and I think it's so, and it's also related to the kind of function that that we have from physics or that we have in images. So I mean, it's true that, for example, the ergodic theorem is true. I mean, we don't have to sample all the configuration, but at the same time, it's true also that we have, let's say, energy landscape, which are not the worst possible energy landscape that one can think of. If one thinks to the worst, then one has really to sample exponential and configuration, but for all practical purposes, we don't. And so I think there is something in the structure of the function that makes exactly what you say. We don't need so many parameters. All right, so what I want to do, so these are all open questions in the case of on which people are working on. So I would like to try to focus on these questions using the length of physics. So I'm going to focus on specific problems which come from physics. So it's not images of cats and dogs, even though at the conclusion I will say something about the images of cats and dogs. But what I want to do is take specific example which come from physics. Actually, I don't want to use a deep network, which is still a black box and with a lot of recipes. What I want to do is to construct a method that will have the same advantage of a deep net, but that we can understand physically. And then in which we can really understand why the method, the property of the method are related to the property of the data and make the method work. All right, so this is what we are going to do. So we're going to focus actually on images now. It's the problem really of, if you want, instead of taking images of cats and dogs, we take images from physical models, so configuration of system, and we take them from statistical physics and cosmology. And then we want to construct a method, so it's not a deep net, we construct a method that we can understand. And this method actually will combine ideas which come from physics, which is the renormalization group, and computer science, which is wavelet and sparse representation. And the aim, which is the typical aim of generative model, is that we want to actually reconstruct oops. No. Why is that? Okay. So we want to reconstruct an approximate representation of the probability distribution associated to the data. So we have all the data. In principle, there is a ground truth probability distribution. What we want to do, we want to reconstruct an approximate representation. Once we have this approximate representation, from it we can sample new configuration, and we can also obtain an effective energy function associated to this probability distribution. So this is interesting in two directions. There is one direction which is really about understanding why generative models work in machine learning. So for example, exactly as I told you, I mean, generative model then can create images of new faces at maximum speed. So with n operation, if you have n pixel. And they can be trained extremely efficiently, even though they have many parameters. So now I will show you actually that this method on this data indeed will have efficient training and samplings, the best possible. So we can sample new configuration, physical configuration. I will show you even at the critical point of the Ising model, in which in principle physical dynamics will have a critical slowing down. But here we can completely kill this slow relaxation and sample with time scale of order 1. And I will show you actually, the nice thing is that not only we can do it, but we can understand in this case why so. Whereas with standard deep net, I mean, you can do it, but you don't understand why you can do it. And then the other direction is really that we want to do physics with this method. So the idea is that, in principle, we want to have a method in which you take the data from experiments or simulation, and then you can reconstruct an effective energy function. This is actually interesting for out-of-equilibrium system. So for equilibrium system, the probability distribution has a Boltzmann law, so it's exponential minus beta times the energy. But if you have an out-of-equilibrium system, well, in principle, you can always write the probability as exponential minus an effective energy, but you don't know what the energy is. And here instead, we can reconstruct it. And then we can also actually do renormalization group directly from data. So it's really a different paradigm. When people try to do renormalization group, in general, well, they first have to find what is the effective theory, then they have to do some approximation. And well, here, the idea is really to bypass this and do it directly from data. All right, so let me tell you what are the data that we are going to consider. So the first case, which is really, this is a benchmark to show that the method works, is we consider the discretized two-dimensional field theory, which associated to the ferromagnetic phase transition. So you have a part which is a Laplacian term, and then here you have a local potential, and the local potential, maybe I should, I say that I wouldn't have used the blackboard, but just to write what the potential is. So the potential V, it has this kind of form. It's the double well potential. So with this double well, so changing the temperature or changing the depth of the two wells, this system has a phase transition, it's known. So at high temperature, the system is disordered. At low temperature, is an order. So the system becomes magnetized. And then there is a critical point between the two. So these are a picture of a 32 by 32 system. Here is at the critical point. This one in the low temperature phase, in which the system is magnetized positively, in this case. And this is the disorder phase. So the idea in this case is that we use it as a test. So we know what the energy is. We can produce configuration with this energy using Monte Carlo Markov chains. Once we have the configuration, now the game is we forget what is the energy. What we want to do is we want, just from this data, obtain an approximate representation of the probability distribution from which we can sample new configuration that we want that are very similar statistically to those ones, and then from which we can reconstruct actually what is the original energy associated to the probability distribution. So if the method works, in principle, we should get exactly the same kind of statistical configuration, and we should be able to reconstruct the energy that we know in this case. And then we also applied it to the cosmological data, which actually, in this case, these are out of equilibrium. So these are results from numerical simulation. And they're important. It's actually having generative model for this kind of cosmological data is very important to put bound on cosmological constants. And it's really open challenge on which deep nets seems to work very well. And so here we show that, I mean, the method that we have developed work as well as the deep nets that have been developed. OK, all right. So you can ask, what about more complex case? What about images of cats and dogs, for example, if you go to computer vision? And I will tell you something at the end. And also other things in physics which are more complicated than just the 5-4 field theory. And I will tell you also something, I mean, what we are doing at the end. All right, so if there are no questions, I will start to explain you the method. OK, so the method, so the first thing is, so the method, as I told you, combine idea from the renormalization group and sparse representation. So let me just remind you a little bit renormalization group, and especially linked with machine learning. So renormalization group is a technique that has been introduced in physics in the 70s, let's say, well, actually even before, but in statistical physics, really to transform scale, to transform the description of a system from small scale to large scale. It has been extremely important in the description of phase transition, and there was a Nobel Prize, but was really an era related to this Nobel Prize. And what you can think is that what the renormalization group does is that hierarchically transform the representation of the system from the small scale to the large scale. Now, you could ask, I mean, why there should be a relationship between renormalization group and machine learning? So this is an idea that came to several people. And it's due to the fact that the machine, and this was already discussed in this series of lectures, what they do, if you consider a deep net, is that the first layer actually are sensible to the small-scale structure. So, for example, edges. And then the more you go deep, the more actually the nodes here, the artificial neuron, becomes actually activate in response to more collective or more large-scale properties. And at the very end, if you do a classification, well, it will tell you, it will just activate if it's a dog or if it's a cat. But this idea that you go from small scale to large scale, from small scale features to large scale feature, is clearly there in this really in the architecture of this network. So the idea is that maybe actually one can try to understand how this network works with changing exactly with the idea of changing scale, exactly like what was done for phase transition now long ago using renormalization group. So I would say that this is an idea, it's nice. And now the thing is, can one go beyond an analogy and really try to construct a real link? And so this is what we did. So I will show you that we are going to construct a method which works in the sense of advantage like the deep nets, but it's really based on RG, and we can understand what it's doing. All right, so let me just remind you, just to set the notation, things about RG. So here, I show you how RG works for the IZ model. So this is going to be a video in which when you do RG, what you do is that here I'm doing changing step. I coarse grain of a lattice spacing. You go to lattice spacing to twice the lattice spacing in one step. So what you do when you do RG is that you go from a description at one scale. Here I call this scale J. So let's say a scale J minus 1. You write the configuration on this scale like a configuration which is the coarse grain part and the small scale fluctuation, or what are called as fast degrees of freedom. And what RG does, in principle, is just you integrate out the small scale fluctuation to get the probability distribution at the larger scale. So this is a description at one scale. This is a description on the scale which is just a little bit coarse grain. So if you express the probability in the Boltzmann way, when you go from here to here, you go from an energy that describes the system at one scale to the energy that describes the system at the larger scale. So just to show you how it works, so this is a video. So this is, if you're normalized when you are below TC, these are the configurations. So you see that you go from a description of the system in which you have spins which are correlated over a certain length scale to a case in which you don't have correlation at all because the system actually flows to what is called a zero temperature fixed point. So the system is ordered. Here's what you do if you are above TC. Again, you are very close to TC. There are spins which are correlated over a certain length scale. Then you renormalize, you go to very large scale, and you get the description of a system which is just white noise because, well, you are in a length which are much larger than the correlation length, so the system became white noise. And here is, if you are TC, well, if you renormalize, well, you flow toward the, what is called the critical fixed point. The system is scale invariant, and this is what you see. So the video that I show here is really related to this kind of theoretical construction. So you want to know how you change scale. And from this point of view, actually, RG is not useful only to understand critical point. It's really important to understand how you bridge scale in physics, so not necessarily the critical point, how a theory transforms when you change scale. All right, so this is the... Yeah.
Can I ask a question here? So in this video, how was the rescaling of the size of the system done? Because as you cause grain,
yes,
you reduce the number of degrees of freedom, right?
Yeah, you mean it's, so actually it was a much bigger system, and then we are zooming.
Yeah, that's my question.
Yeah.
So what is actually done? You start from a very big system?
Yes, and then you go down in scale of twice each time.
I see. So you reduce exponentially fast
yes.
the number of degrees of freedom.
Yes, exactly. Yeah. All right, so this is just renormalization group in a nutshell. And by the way, I mean, this video is not myself. It's someone else. It was just for pedagogical reasons. All right, so this is the notation. So this is the scale. Is the sides at scale j minus 1. This is sides at scale j. Here is the transformation. And now, renormalization group in a nutshell, what I want to tell you, actually, there is a crucial ingredient in the normalization group, which is the reason why the normalization group works, which will be crucial for us. And, well, as I told you, what renormalization group does is you integrate out fast degrees of freedom, and then you rescale, and you obtain the theory at a larger scale. Now, and this is, well, it's just a sketch of a flow in, let's say, in 3. Well, here I cannot do it in many dimensions, but will be the flow of the coupling associated to the energy. Now, what I really want to stress is, so why renormalization group works? So you have to think that renormalization group has been introduced to treat critical phenomena. So critical phenomena are singular problem. Singular because, well, you know that if you change, for example, the critical temperature a little bit above or a little bit below Tc, well, the system is changing phases. So it's really the behavior, or the collective behavior of the system is changing singularly when you are close to Tc. So if you try to do perturbation theory to describe this state, of course, perturbation theory fails badly. And it's normal if you have a singular problem and you try to do perturbation theory in a coupling, then, well, you're going to get singularity everywhere. Now, renormalization group, you have to think people never do it exactly except in a very few cases. So you do approximation within RG. But if you do approximation and perturbation within RG, then it's fine. If you do it just for the bare problem, for the bare energy, then it's not fine. You have divergence everywhere. So why approximation are fine within RG? So, and this is, I think, is one of the crucial points why actually RG work. Well, they are fine because what you have to think is that what RG does is this transformation from one scale to the other. When you do this transformation, you integrate out what are called the fast degrees of freedom, or the small scale, what are the fluctuation of the field, which on the small scale at the scale at which you are. Now, this actually, the composition of the field in the coarse grain part and the fast degrees of freedom, it's very important in the sense that you always work, when you do RG, on the fast degrees of freedom, which are the ones which are not singular. They are not long-range correlated. And on this one, on this field, you can do approximation. So you don't do exactly this integration, you do it approximatively, but since you are doing approximation on a field which is not singular, there is no problem. And I will show you graphically, actually, why so in a minute. Okay? So this is really the key, one of the key things about RG, is really and why it works. And it will be a key also for us. So now let's see our method. So our method is, so what we do is, in a sense, we proceed. So you have to think we have data, and we want to reconstruct the probability distribution and the energy function from the data. So we will proceed exactly the inverse way with respect to RG. So what we are going to do, so well, first, so we have, let's say if you have a field, we decompose the field in the coarse-grained part and in the fast part. And just to show you visually also how this decomposition is done, let's say that you have a field here on an L by L lattice. You can decompose it in a coarse-grained field on an L by 2 by L by 2 lattice, and then 3 other fields in 2 dimensions, and these are called the wavelet field. So this is an exact orthogonal decomposition, which is based on wavelet theory, and well, in a sense, what physicists did it before, and actually, if you look, and this is something that I discovered, if you read the original paper by Wilson, in which before he did the epsilon expansion, but really the original paper in which he did the Wilson method, it's incredible because he actually introduced Shannon wavelet, I think 15 years before that wavelet theory was introduced. So in his paper, which of course was about RG, he reintroduced the main idea about wavelet theory, but then he goes on about doing RG. So, but then, of course, wavelet theory has been developed. So there are a lot of work on how actually decompose, well, orthogonally and in the best way, the field in a coarse-grained part and in a fast part. So just to show you typical wavelets, so the wavelet decomposition is a kind of it's a kind of generalization of Fourier decomposition. So if you use as a decomposition the Haar wavelet, so Haar wavelet you can think is that if you have a field, phi1, phi2, phi3, phi4, phi in 1 dimension, then you can decompose it saying that phi1 plus phi2 divided by 2 is your coarse-grained field in 1 point, and phi1 minus phi2 divided by 2 is the fast part. This would correspond to the Haar wavelet. And if you think in terms of RG, this will be what we call Kadan of real space RG. Now, if you use wavelet in which instead you, which are defined in this way in Fourier space, this just corresponds to what Wilson momentum shell, in which you take the Fourier expression of the field, and you decide that there is, let's say, a width, a window at high frequency, which will be called the fast component of the field, and all the rest is the coarse-grained part. But actually, there are actually wavelets. In the wavelet theory, both these cases are not good, because these are very localized in real space, but are very delocalized in Fourier space. The Shannon wavelets are very localized in Fourier space, but they're delocalized in real space. And the nice thing about wavelet theory is that they found wavelets which are both localized in real space and Fourier space, which are the ones that we are going to use. And all right, so if you have this decomposition of the field in terms of wavelet parts, so the fast part and the coarse-grained part, you can always write the probability distribution of the field at the scale, at the smallest scale, as the probability distribution of the fast degrees of freedom, so the wavelet, given the coarse field, times the probability of the coarser field. So this is just an exact identity, but we are going actually to cascade this identity, and this is going to be useful. So what we are going to say is that the probability of the field, we are going to rewrite it as the probability, so thinking, we use this, probability of psi1 given phi1 times the probability of phi1. Now, probability of phi1 is the probability of the field when we have just coarse grain of 1 step, but then we do it again. We use this identity again for p of phi1, and then we do it again for p of phi2, and so on and so forth. And so if we do it, we can rewrite the probability distribution in an exact way. So this is nothing deep, it's just a way to rewrite it, as the probability of the fast degrees of freedom on scale 1, given the coarse-grained degrees of freedom on scale 1, times the probability of the fast degrees of freedom on scale 2, given the slow degrees of freedom on scale 2, and so on and so forth, until we arrive to the probability of the coarse-grained field, which has been coarse-grained over the whole sample, so this is just one variable. Now, this is a way to reparameterize the field in terms of all the fast degrees of freedom at each scale, and then there is the last scale on which we have the coarser field. And now the way in which we reconstruct the data, the way in which we reconstruct the energy and we get a new method to do sampling, is that we are going actually to estimate all this conditional probability. So this is an exact representation of the probability distribution. And what I want to say is that if you try to, if I do the analogy with perturbation theory and RG, if you try to estimate directly this probability distribution, then it's going to be very bad, especially if you have a long-range correlation. Instead, if you try to estimate first this one, then this one, then this one, and until arrive to here, all this conditional probability, then the problem will become easier. And it will become easier in the sense that you can estimate easily from data this conditional probability, but it becomes also easy for sampling, in the sense that if I sample now, what I have to do, I first sample, once I have all those, I first sample the cursor field, the value of the cursor field, then I will sample the fast degrees of freedom on scale j, then the fast degrees of freedom on scale j-1, and so on and so forth. And since these are fast degrees of freedom, I can sample them fast. It's just their property. So this means that when I sample in this way, I will be able to sample on time scale of order 1, even though if I try to sample by Monte Carlo Markov chain this probability, the time can diverge because the system is at the critical point. So this really is the crucial part of our method, is that, again, we really work only on the probability of the fast degrees of freedom on each scale. And because we work on them, we can estimate them easily, and we can sample them easily. And in a certain sense, what we are doing an inverse RG, in the sense that when you do RG, you integrate out the fast degrees of freedom at each scale to get the probability at a larger scale. So you always lose a little bit of information. Here, what we do is that actually at each step, we retrieve a little bit of information from the data. So first, we estimate from the data this one. Then we use the data to estimate this, so we get the representation of the probability at the smaller scale, so we get a little bit more information. Then from the data, we get the conditional probability to go to the smaller scale, and progressively, we use all the information in the data to get this P of phi 0 once we know all the conditional probability. Is the method clear? All right. OK, so just a little bit more detail, and then when I will show you the result. So I mean, of course, we must have a model for this conditional probability. And in the simplest case, the model for the conditional probability that we are going to use is a model. It's related to a model of the energy function at each scale. So it means that at each scale, the model of the energy will be this one. So there will be a bilinear part with a general operator, which we take a translation invariant. So it's a generalization of the Laplacian. We'll have a potential, which is, it's a function of phi, which is defined at each scale. So you have to think exactly like when you do in RG, you have to define what is the class of energy for which you study the flow. Here we have a class of energy for which we define a conditional probability. So this one is kind of standard. And then we have this term. So this term actually, it's a sum over all scale of local potential defined of the local field, but the local field at that scale. So why we do so? Because actually, if you take an energy like this and you go through just the conditional probability law, what you get for the conditional probability, and this is, I think, it's really the key part, which is you get a form for the conditional probability of the wavelet field, which is local. Local means that the wavelet field at scale j will interact, but will interact only locally. So we will not have a long-range interaction. So at each scale, this probability, conditional probability, it's a local model in which you have, I don't know, nearest neighbor, next nearest neighbor interaction between the wavelet field, but not more than that. And this, I think, is, if you want to generalize what we are doing, of course, you can forget about this for some problem, but I think it's really the key ingredient in the method is that at each scale, the interaction between the wavelet field is local. And then, well, so this we estimate by maximum likelihood from the data. And then, well, if we want to compute the energy function, we must also obtain what is the normalization factor, which is the free energy, and we do it by regression. So I'm going a little bit fast because it's technical, but I can come back. It's nothing difficult. So once we have estimated all this conditional probability, now what we can do is that we can actually, we have a generative model, we can create new configuration, and we do it, as I told you, well, we have estimated this, so we can use Monte Carlo sampling to sample phi j. Then once we have phi j, we can use Monte Carlo sampling to sample psi j minus 1, and so on and so forth. And so we get the configuration in this way, a configuration phi 0. And then not only the generative model, we can also get the energy of the system. If we know all this h bar and all this f, we get the energy which is associated to the probability distribution. OK, so why actually, in a few words, this system is easy to estimate, the parameter of the model. And sorry, maybe I should say what are the parameters of the model are the constant we define this operator. We get a representation for this function. We discretize the function, so we have a representation in terms of parameter of this function and those functions. So all these parameters are estimated. Why we can estimate them fast, independent, even if the consider configuration which are at the critical point, so which have long-range correlation. And why we can sample fast. Now, I'm asking this question because if you try to do it just from directly, so you say that the probability distribution is exponential minus something which resembles the energy of the phi-4 model, and you try to fix by maximum likelihood the parameter of the model, then at the critical point, this is going to fade badly. Again, for the same reason that I told you before, you have to be super precise because this is a singular problem. So what is called the learning rate or the step in your gradient descent of maximum likelihood will go to 0 when the system is in the thermodynamic limit. And similarly, even if you have estimated correctly this parameter, if you try to sample new configuration by Monte Carlo, this will take a time that diverges at the critical point because you have critical slowing down. So we circumvent these two things. And why we can do it, I mean, it's in a nutshell, is really because we always work actually on the fast degrees of freedom. And because we work on the fast degrees of freedom, this probability, conditional probability, are not singular, even at the critical point. And so they are fastly, you can estimate them fast, and you can actually sample them fast. So we can show it explicitly, I mean, rigorously, in the sense of mathematical rigor in the Gaussian case, and we can show it with, let's say, methods based on theoretical physics in more general case. But the essence is really this one. We work on the probability of the fast degrees of freedom. So it's easy to they are easy to estimate, they are easy to sample. All right, so let me show you the result. Again, I recall you that the result means that we take data generated from the phi-4 field theory, 2D, or we take the cosmological data. Just to give numbers, these are 32 by 32 images, but we can scale up, go to larger images now. And there are roughly 10,000 images, and we have to fix 250 parameters. Just to say that if you use deep nets to do this, I mean, the number of images that you have to use is much larger, and especially the number of parameters that you have to use is much larger. And this is, well, it's why also this model is useful, is that since we have a theoretical understanding based on physics, we can use much less model. So in a certain sense, our inductive bias is much stronger. All right, so let's see how it works. So here is, in the case of the Ising model, these are the true configuration. These are the ones generated by the method once it's been trained. Well, as you see by the eye, at least by the eye, they look similar at TC, above TC, or below TC. Now, the interesting thing is how actually, when we estimate the local potential in the model at each scale, how it flows. So normally, when you do RG, you flow from small scale to large scale. Here is exactly the opposite. You flow from large scale to small scale. So at the beginning, the potential is Gaussian. If you are, let's say, above TC, it's normal. Very large scale, the system is Gaussian. But then when you go down in scale, you find, I mean, the double well potential because it's normal. At the microscopic scale, the local potential is a double well. If you are at TC, well, what you see is that, well, again, the system remained for a long time, actually, very close to a certain form. And this is the sign that the system actually is flowing very close to the critical fixed point. If you are below TC, here is something which is really nice. So you start from something which is asymmetric. This is normal because you feed the system configuration which are only positively magnetized. So which means that, well, the magnetization should be positive. And so it means that the local potential at large scale will favor configuration which are positively magnetized. Then if you run so if you estimate and if you go down in scale, actually you find again, well, I mean, this is just, it's just because we actually cut here. But what you find again the double well. So this is actually something which is very interesting in the sense that you feed the system all configurations which are magnetized, so with have broken the symmetry, and the system actually is able to see that the original energy was symmetric. And I mean, of course, there is no information whatsoever to the system that this configuration comes from an energy which is symmetric or almost symmetric. But the system discovered that actually to represent the probability distribution associated to these images, you must use a potential, local potential, which is symmetric. So it discovered that actually there was a symmetry that has been broken without knowing that there was a symmetry, because it just gets a broken symmetry configuration. Which, to me, I mean, it's really a very non-trivial test. What the system is doing, I mean, why, you can ask why it's able to do so. Well, it's because, of course, it gets configuration which are magnetized, but within this magnetized configuration, you have fluctuation in the other phase. And actually, to describe correctly the fluctuation in the other phase, well, the system discovered that for the small-scale fluctuation to be reproduced correctly, the system must come from a double well.
Doesn't quite make it to fully symmetric.
Yes, I agree. It's not exactly symmetric, but this is, in a certain sense, is normal, in the sense that we have a finite size system. So if you feed configuration which are all positively magnetized, it means that there is a small magnetic field, which actually will go to 0 when you take the thermodynamic limit. So it's correct that it's not exactly symmetric, but because the system is finite size. And so this is the comparison between so this is the double well that we use to reproduce, to create the data, and this is the double well that you reconstruct with the method. So you see, it's extremely good. These are the eigenvalues of the bilinear operator, which is just a Laplacian, discrete Laplacian. One is the true one, and the other one is the reconstructed. And again, you see something which is very good. So this is just to show you that our reconstruction works extremely well. Now here is the part which I think is even more interesting. Is the first thing is the absence of critical slowing down. So if you are at TC, and if you do dynamics of a physical system, so for example, Monte Carlo Markov chain, it's known that the system takes a very long time to equilibrate. The longer, the larger is the system. And here's what you see. Here is the correlation function of the field using direct Monte Carlo simulation. And for different temperature, and you see here we are approaching TC, and you see that it takes longer and longer time to go to 0, which means a longer and longer time to decorrelate. Here is, well, what is the wavelet field? If you look at the correlation function of the wavelet field, well, as you see, nothing happens. So even when you approach TC, actually, the time scale is just to reduce a little bit. So if you look at the time scale, and here is changing T and going to TC. Here is exactly TC increasing the system size. And what you see here is that here, if you have direct Monte Carlo simulation, this is increased. This is known, critical slowing down. And here is the time scale that we have in sampling from our method, which is just not moving. And again, this is really due to the fact that we are always sampling the fast degrees of freedom. And here is for the estimation. If you do direct estimation, so if you try to estimate the parameter of the model from directly, then you get that the system actually, the gradient descent that you do is very slow. But if you look at the gradient descent that you do when you use our method, when you estimate only the conditional probability, then it becomes very fast. And the reason, again, is really that we work on the wavelet field. Maybe something that I didn't show that I would like to show, because I think it's something that I didn't realize when I was a student in physics. But you can see that the wavelet field is very simple. You can do approximation on it. It's not a dangerous variable. It's because, I mean, you see it visually. So when I have this field, and then I look at the coarse-grained part and the short and the wavelet field, you see the wavelet field almost look like white noise. There are no long-range correlation. Nothing is difficult on this one. So it's clear that you can do approximation. It can be sampled fast, and its probability can be actually estimated easily. All right, so okay, given the time, I will go quick actually on the cosmological part. So in the case of the cosmological part, we don't know what the energy is. It's not known. So what we can do is that Well, first we have the training and the synthesis, and we can show that we are as good as the competitive model, like deep nets in this case. We can look at, for example, the probability of local fields. So in this case, it's known that there are long tails actually in the probability, and these are important. And we show that, well, you see it here, that the training data, so the true data, and the synthesis both of them have this tail. And we can also study the flow of the energy potential. And, well, in this case, I don't have the same intuition that I have in statistical physics, but I think it's the first time that has been reproduced an effective energy with effective potential for this cosmological case. The interesting thing is that in this case, we must use these long-range potentials, which are the potential which couple the field on larger and larger scale. And this was, I mean, without these long-range couplings, we can't reproduce this energy. So this is something interesting compared to usual RG. In usual RG, the theories are local at each scale. Here, actually, we can go beyond this. As long as we are local on the fast degrees of freedom, we can get something which is non-local in the real field. Now, what I would like to discuss in the last 5 minutes are two aspects. So first, going back actually to what I discussed at the beginning. So there are several questions on why this method works. So how faithful is the representation? Well, I mean, are they efficient and stable? So they seem to be efficient and stable, but why so? And do they reconstruct the Hamiltonian? Well, in many cases, actually, deep nets cannot reconstruct the Hamiltonian. They just able to generate, to do sampling. And I mean, all these questions can be actually answered in our case. It's really, well, with our method, we can show, at least in some cases, that it reproduces accurately the underlying probability distribution. We understand why it's efficient, so why you can estimate fast and sample fast, because you always work on the fast degrees of freedom, and you can reconstruct the Hamiltonian. So, I mean, the conclusion of this is a first case in which you can really understand the interplay between the data and the architecture, in a sense. So the architecture of the deep nets, as I told you, has this hierarchical structure and works on small scale and then progressively on large scale. And this is what we do. What we do in this model is that we really estimate probability distribution at each scale. So the fact of decomposing at each scale is really the key. And I think in physics, for images that come from physics, is quite natural and is embedded in the context of RG, is that you start from an Hamiltonian that has local interaction, and then through the dynamics, you generate configuration, and if you go to different scale, these configurations are still described by the theory that remain local at each scale. Now, this, of course, you can ask, what about images? So why images should behave in this way? And so, so for images, if you try to apply this idea for images, they work to some extent. And the idea is the following. So if you have the probability of phi 0 for an image, you can always decompose in this way. Now, the interesting thing is that, as I told you, we have so in the case of physics, we have an idea of how to parameterize this probability law based on some energy function. Now, of course, in the case of images, I mean, it doesn't make sense to consider an energy function with a Laplacian and the local potential. But what you can say is that you can represent this with a model which is local on the fast degrees of freedom. And if you do so, so if each one you do it with a local model for the fast degrees of freedom, then you almost get the good result. Actually, to get the good result, what they realize in this paper is that you can do it at each scale, so a local model on the fast degrees of freedom at each scale, and then when only at the very large scale, you have to you have to consider a model in which you couple degrees of freedom to all scale. So it means that an image, for example, a 300 by 300 image, at each scale, you can use this local model. And when you arrive at 10 by 10, you have a coarse grain at 10 by 10, then you have to use a completely connected neural net. So in some sense, there are some features that you cannot capture by this local model. And maybe this is normal. Maybe in a phase, there are some features that are really described by very collective properties. But many things, many information within an image are actually can be just captured by the same model that we use for physics, just, well, a generalization, but just a local model for this probability distribution. Now, this is for computer science. What we want to do in the following is really apply this method to a non-equilibrium system. So in non-equilibrium system in statistical physics, well, you have a system which goes in a steady state. Well, we don't know what is how we can work out what is if there is an effective energy description of the model. So just to give you an idea, well, something that has been studied a lot in recent years is what is called active matter, in which you have particles that interact in some way, but they have an equation of motion that break time reversal symmetry. So they go to a steady state, but the steady state have entropy production, so it cannot be described by the Boltzmann distribution. But still, there is a steady state probability distribution. So you can ask, what is the energy? Can we understand it? So here is an example. This is a case, for example, in which system is active, but not so much. Here is a system which is very active. And here you find this phase separation changing parameter, which is more or less usual. And here you find the phase separation, which is quite weird, in which you have a micro bubble of one phase within the bubble of the other phase. And so what we want to do is really to study this, both in terms of what is the effective energy that describe this phenomena, and also we want to do actually RG theory. Because now, directly, just producing data from simulation, or if you get data from experiment, then with our method, we can do RG. So something that I didn't tell you is that for the 5-4 model, for example, we can get the critical exponent with our method just from data. It's a new way, actually, to get the exponent. And now, this is in active matter, and then if you go further ahead, more difficult problem would be two-dimensional turbulence, and this is something which we are thinking about. But OK, this will be the next step. This will be the first step, and then 2D turbulence will be the second step. And so with this, I thank you very much for your attention.